So let's get started. So I'm going to talk about something called the FMQ platform, which is something that I had developed. As Jeff said, my name is Michael Tiller. My company name is actually Xogeny. So this is a source of endless confusion. Jeff is not alone. It's Xogeny. In fact, and then in another bit of irony, I was telling one of my former coworkers, so yeah, it's Xogeny. It's from the Latin. And he said, no, it's from the Greek actually. I was like, oh, okay, all right. So that shows you how little I even know about my own company. So anyway, it's Xogeny. It's an actual word. Okay, so. That no one knows. So fortunately, Google didn't know it either, so I own the Google space on this. So I'm gonna stick with it. Okay, so Xogeny. So this company is born out of my frustration with not being able to get the most, what I think are really interesting technologies from the tech industry into engineering. I'm fond of pointing out that 1988 or 1998, the world really changed in terms of the way web technology sort of took over our daily lives. We barely felt a ripple of that, I feel, in the engineering world. We don't get the advantages of those kinds of technologies. And so I started a company mainly because I felt like I wanted to explore this idea of bringing all this technology to bear on engineering problems, which is, of course, my background, right? So all my degrees are in engineering. I worked as an engineer pretty much my whole life. But I've also worked on software, and I thought it was such a shame that we had this gap between the technologies that existed in the high-tech world and what we had to bring to bear on our engineering problems. So FMQ, which is the name I gave to this tool, is actually essentially FMI running in the cloud. So the idea is that you should be able to build models and then be able to easily use the services that are already out there in cloud computing to be able to execute these models. And so that's essentially what it means. And the queue is just a play on word to the word queue, like people in a line queue. So you can essentially batch submit things to this service and process FMI. So anyway, I wanted to start by pointing out some what I think are interesting architectural shifts in in computing. You may have noticed about 10 years ago or so that suddenly your computer had more than one CPU. And that's partly because we have this problem that we couldn't make CPUs, we couldn't increase the density of these transistors, and we had to start sort of branching out and having multiple, essentially, CPUs. And this has sort of broken the mold of some of the sort of classic computer architectures, and it's been an issue for simulation as well, because a lot of simulation codes are not really necessarily designed to run, at least system simulation stuff, it's not really designed to run across multiple cores. It tends to use a lot of sort of essentially serial operations. So how can we adjust to the fact that we have now all these CPUs that we can bring to bear on these kinds of problems? So the idea here is that in order to think about the future and how we're going to make use of the fact that we have these large cloud-based platforms for running simulations, what is that going to mean for us? And I think I tried to summarize here a couple of things that I think we're going to need to start thinking more about how we can pull together our analyses based on loosely coupled simulations, make things more parallel, take advantage of these kinds of cheaper computing resources to do things like Monte Carlo analysis and design of experiments and model reduction. So I think there are a lot of opportunities here with essentially what we have is essentially computing on tap. We can just get as much computing as we want and we can get it cheaply. So I developed this FMQ platform, which is a proprietary platform, and it's a platform for running FMI compliant FMUs in the cloud. And as an engineer, I knew that this was possible, and I'd worked on some projects where I really needed to be able to do this kind of thing, to be able to take a simulation and just run a bunch of them for a bunch of different parameters, and I knew it was possible, and since I knew Amazon, for example, has this enormous cloud. It's enormous. It's like 5 times the size of any of its competitors. So how do I get on that, right? And I decided, okay, well, I'm just going to build the tools to do that. So the whole point is cloud computing is a commodity, and it should be a commodity for us in the engineering community and specifically in the FMI community. So what I did was I developed this platform that not only can run these simulations in the cloud, but it also handles the sort of the data management of it. So you submit these things, it keeps track of what jobs you've submitted, what results have come back, the relationship between the simulation and any results that it generates, and it's all sort of traceable and provides some level of provenance as well. I mean, so you can really figure out where data came from. So it does all of that, and then originally I was sort of thinking about this as a way of being able to run large numbers of simulations, but sort of a funny thing happened when I started doing that, which is I needed a way to demonstrate this idea to people, and so I started building these web-based user interfaces that leveraged this cloud computing, the fact that you could do simulations in the cloud, to demonstrate stuff. And so, yeah, so anyway, so I got down this track of web-based simulations, so I want to talk about that a little bit. One of the things that I've always found very compelling about modeling, I mean, I've been doing model development for a long time, is this idea that when you build this model, and it's got all these parameters, you can start tuning them, you can tweak them, you can explore this design space, and it's almost like this, this immense virtual world where you can go around and explore, like, what if I did this, what if I did that? One of the things I came to appreciate, and we've seen this touched on by several of our speakers, was that as an expert, that's really compelling. What I found was that then there's a sort of, a flip side to this, which is for non-experts, this wide open set of possibilities is not necessarily such a great thing. They don't want lots of wide open possibilities. It's very disorienting to them. I mean, what should they do? They want things that are going to sort of hold their hand through this process, guide them in a way that as a model developer, I would find constraining, but for them, it's something that is sort of necessary. The thing is, there's this landscape of infinite possibilities, and I thought this was kind of a funny visual. This is why people don't necessarily like infinite possibilities, right? So you look at the complexity of this, and I'd hate to be the roadie who had to set that up and get it right every night. So this is Keith Emerson, by the way. So the thing is, there's a time and a place for complexity and for having lots of knobs to turn and options. But what I find is that, and I found this even when I was developing models, that I really wanted a way to be able to take all of this knowledge that went into developing these non-trivial models and making it accessible to people who were non-experts but could really benefit from that, and to get a feedback cycle where they then appreciated the models and the expertise that was essentially being deployed to them enough to sort of speak up and say, hey, these models are great. We should get these guys to do more models and sort of get this feedback loop going so that we think of these people as customers for model development, and we keep them happy and we keep them fans of ours. So how to do this? Okay, so I mentioned this whole infinite possibilities thing and the idea that we need to make interfaces for people that are more customized for their workflows and the way they think and holding their hands through things. So I think Apple has done a really nice job on a lot of their products in understanding this. So I'm going to talk about analysis applications, and normally when I give these presentations, I actually do the whole thing. These are web-based applications. I would actually get out my web browser and show you. Because I was a little uncertain about whether they would even allow Wi-Fi in a movie theater, it seems like that would be kind of a crazy thing. I made videos of these things, so we're going to just go through the videos. But I want to talk a little bit about what I think of when I put together these kinds of analysis applications. And I've done a couple of these for different customers. I'm going to show you some sort of standard demos, non-proprietary stuff that I can share with you. But in general, I think the first thing to recognize is that models themselves are not applications. And I'll talk about what I see as an application. But a model by itself is not sufficient to sort of hand over to somebody and say, here you go, have fun with it. Unless they're an expert. The models themselves are just these complicated functions that exist inside of the application. The analysis itself, or the analysis application itself, should include obviously the models, and this is where you've heard many people talk about this idea of model deployment. This is where I see that coming in. We need a way to get these models into these applications so that non-experts can use them, so that's part of it. You need business logic. There are all kinds of constraints you might want to impose. There's this sort of hand-holding. There's the kind of wizard interfaces that step you through a process going one step to another that you need to capture. And there's also this data management aspect. And I'll try and demonstrate some of these in the demos actually. These kinds of applications should really focus on the business questions that people have to answer, right? I'm a model developer. I love playing around with the math and the differential equations and the index reduction and all of that stuff. But at the end of the day, if you want modeling to be relevant to the enterprise, you have to, address their needs and their concerns. And one of the things that I've done in addition to complement this FMQ platform was when I started doing these kinds of applications, I wrote what I think of as a compiler. It's essentially a model to application compiler. And so what it does is it starts with an FMU, which might come from a Modelica model or it might come from some other environment. But I take this FMU and then run it through this model compiler, and that with plus a combination, the FMU plus a combination of templates ultimately yields the application. So when I build these applications, I don't actually write the applications myself. What I do is I write a bunch of templates and some other data structures, and then this compiler generates the applications. And ultimately, although the FMQ platform has a RESTful web API for submitting jobs and so on, I also created this JavaScript interface to it to make it simpler that handles simulation and data management, and that's leveraged behind the scenes in these applications as well. All right, so this is a video of a robot model. This is the Modelica R3 robot model, if you're familiar with it. What this is doing is a web-based application. You push these buttons and it's commanding this robot to go to different points in 3D space. Now keep in mind, this is all done in a web browser, all right? So you don't normally see web applications that look quite like this, but if you have a version of Firefox, you can just run this thing in your browser. And you see it's solving the 4,600 or so equations that exist behind the scenes here. This part, the actual robot simulation was done in Virginia, and the rest of this is all being visualized on my desktop. So you can interact with this. You see a pretty decent level of interactivity here as you essentially adjust the set points. You can see the graphical results streaming by as the thing's running. You see obviously the 3D rendering of the thing. The scenario here would be something like an operator in the loop training application or something where they have a complex model like a nuclear power plant and they want to practice startup procedures or drills for handling emergencies or something. And you can see here, obviously, that you can see data coming out. You get a projection of the 3D results for this thing. You can look at different axes in the model and the results associated with different axes. So all of this is essentially a Modelica model converted to an FMU, and then running in the cloud, not on your desktop, in the cloud, with a web-based user interface to interact with the simulation. Okay, so next demo. Now the first two demos, I will admit, are kind of toys. I put them up there mainly so people really appreciate what I think are the interesting possibilities that you have combining the cloud with modeling with web stuff. The third application, so just hang with me. So in this one, I was at a conference 2 weeks ago. It was actually academics talking about modeling and the modeling curriculum. And what I did was somebody asked this question about variability. So what I did was I took this, and since I did this over the weekend actually, I took the Latka-Volterra model, and these are the parameters for the Latka-Volterra model, and these are some variabilities here, some uncertainties. And if you run the model without considering uncertainty, you get these trajectories, right? So this is a predator-prey model. So as essentially the prey, the predators die off because there's not enough prey, the prey increase. The predators come back. As the predators come back, the prey die off again. So that's what's going on in this. But you see I've got these uncertainty parameters around some of these values. So I can actually go in and say, let's run 20 simulations of this thing, right? So what you're seeing here is it shows you the baseline results to begin with. That's the dark blue line, the dark red line. But then it starts layering on, using a Monte Carlo analysis behind the scenes, a bunch of other potential trajectories that are generated based on these uncertainties. And so now you get a sense of an envelope around which your potential solutions could be. And so what I think is interesting, I mean, for example, in this is that this professor who asked me, was talking about this, was saying, students don't really have a sense of they think a model with a bunch of parameters has a solution, but in fact it has multiple solutions, right? Multiple possible solutions depending on how accurate your input data is. And so here by the way, I just changed, this is another example where I changed around the uncertainty about the initial conditions as well, just added that in here, and then I'm running another analysis, and again you see these sort of figures showing up. And what this is doing is it's using technologies that are already in web browsers to render these kinds of things and give you this overall sense, and you can see here it's running all these jobs. Give you a sense of what the uncertainty is. Now keep in mind, one of the nice things about the cloud computing here, I only actually used my development server, so that's just essentially one machine when I did this, when I put this video together. But if I were doing a fuel economy study and I wanted to do some uncertainty around it and I wanted to run 100 jobs, I mean, I can turn that around in basically the same time it would take me to do one job. Amazon charges you by use, and they don't care if you run 100 jobs at once or if you run 100 jobs one after another. It's the same cost. So the point is, these kinds of figures for simulations can be turned around really quickly. So now, before I run out of time, I have one more of these, which is has a little more depth to it. And I have to say, I want to first acknowledge Modelon, because this is actually, I told you that the compiler requires an FMU to go into it to compile, and it's actually their model that I used in putting this together. But let me show you this. Now this is more like a real engineering application. You see a bunch of subsystems. This is for vehicle thermal management, and you see here there's a heat exchanger stack, a car, and a transmission. Again, this is all running just in a web browser. No plugins, no Flash, nothing. This is just normal web browser. This is essentially a rendering of some geometric relationships between heat exchangers and the heat exchanger stack. And it's tied to this Excel-looking interface here, but what's nice about it is that as you update the variables here, instead of just dealing strictly with this Excel-like interface, as you update these numbers, you get a real sense physically of what these numbers mean and how they translate into the geometry of this system. And you can see, like, when you make a mistake, and that obviously doesn't look right, you say, oh, okay, I did something wrong there. You can, of course, layer all kinds of information into a user interface like this. So you can use techniques like this accordion control to do this. You can jump around to other subsystems. Note all this information here. This comes from the Modelica model via the FMU, which has this in the model description XML stuff. And that all ends up in the application. And it means if you go back to the model and change these default values, or you change any of these descriptions, they'll come back into the model when you recompile, or to the application when you recompile it. You see even the limits, for example, these are from the Modelica model, but they're enforced by this user interface automatically, so I don't have to write code to handle all these cases. If you have some bad data, you'll see that you can't, for example, simulate this. You have to go back to the form where the data was, enter the, correct it, and then you can go over and you can, change other parameters, for example. And then run a simulation. So I'll get to that here now. So we go off and we run the simulation. And this simulation took like 5 or 10 minutes or something, so I'm sort of skipping ahead here. So I'm just gonna sort of flash in some results here. So it's not actually running in this case. But you see, results. You can put together plots. You can even put textual information summarizing what happened in the simulation, all in here. So you can do a lot of stuff, obviously, with reporting out on simulation results. You can then go back and change the data, but there's something important that's going to happen here as I change this data. You notice now that the results went away because I changed the data, so that those previous results weren't valid. So I get new results, but I can click on this history button up here. When I do that, you see that this actually represents the default data that we started with, and this represents some of the modifications that I made. So as I go through and change these things, you get new, essentially new simulation results, new data sets and new simulation results. And I can actually skip back and forth between those. So you'll see here in a minute. As I click on these different spots, I can look at, for example, what was the difference between this simulation and the default set, and it shows me what it is that I changed, for example. I can then go back and you'll see, notice I was sort of selecting that middle node in that diagram. If I then go back and make a change to my model, something like that, go back and say simulate again, what you'll see is then once that simulation is completed, I'll go up and look at the history, and you'll see now that there's this branch here, right? So from this data set, I went 2 different directions, 2 different design changes. I can go back to the original default data, or to this data just by clicking. You can't quite see probably, but there's a dark circle there indicating it's selected. You see again, the data disappeared, by the way. I can now make some transmission study where I go in and I change the data about the transmission, and I go back and I say simulate that. And as I'm doing this, it's keeping track of all of this stuff. So you see this is green right now. It'll turn blue when the simulation results are available. So that actually will just pop in here in just a sec. But the idea here is that you have this history, and this is one of the consequences of sort of centralizing all of this simulation, is that you not only get the simulation stuff being done in the cloud, you get to leverage a lot of stuff that you have with respect to capabilities with respect to databases in the cloud as well. I think there's all kinds of capabilities out there for the technology that we're not getting to leverage in engineering. I think there's a competitive advantage out there for people who are willing to sort of take the chance on these kinds of ideas. This is all proven technology. It's proven every day by big tech companies. It's really a shame to me that engineers don't benefit more from these kinds of capabilities. So I think model development ultimately needs to break free of the desktop, embrace a web-based approach, and ultimately make sure that modeling has a greater impact on model development process. So I've sort of committed my company to embracing these sorts of brave new ideas, and we're going to see how that pays off. But you know, there's that saying, you should be the change you want to see in the world. So I'm trying to do that. That's it.